Hey guys, let's do a little review of gravitation. We'll start with the concept of gravitational force between two objects of different masses. These objects could be planets, but don't necessarily have to be. The first thing that we should describe is the fact that the forces on the two objects are always going to be equal, even though the two objects don't experience equal accelerations. Now, it probably doesn't make intuitive sense to you that two objects with different masses should exert the same force on each other. But even if you don't believe your intuition, right, the math shows you that, well, it doesn't matter which order you multiply the m's in, the force is going to be exactly the same. You and the Earth, for example, exert equal and opposite forces on each other. Your accelerations, though, are very different because if you set this equal to, let's say, ma for you, well, you experience a much larger acceleration. If I set that equal to big ma for the Earth, then the Earth doesn't experience much acceleration at all because you're dividing by an enormous mass right there. The next concept is the gravitational field, which is really actually just the same thing as acceleration due to gravity, because you'll notice what's really sort of missing from the gravitational field equation is that little m right there. In other words, if I do little m times g, should be g with an arrow over it, well, that's the same as the force of gravity, and we've been using mg for gravity for as long as we've talked about the force of gravity in physics class. The gravitational field at the surface of an object is called surface acceleration. As you can see from the equation, the field and force and most things in gravity get smaller as you move away from the object, so that you have the maximum gravitational field at the surface of the object and, a smaller one as you move further away from it. The large MEP in this diagram here has a large gravitational field. The little MEP has a tiny one because the gravitational field of an object only depends on its mass. So in this equation here, if I plug in the mass of the big MEP, that will be its gravitational field. If I plug in the little m for the mass of the little MEP, that will be its entirely trivial gravitational field. I don't know if it's going to come up, and I imagine it won't, but if they ask about the gravitational field inside of a planet, it gets a little weird when you get in here into the interior. It starts actually looking sort of like a Gauss's law problem, where if you consider only the mass enclosed within a certain radius, that's what actually counts in this mass term right here. And so actually, if you made a graph of gravitational field as a function of distance from the center, it'd look like, right, increases linearly as you move away from the center, and then does the whole inverse square thing as you move away from it. Remember, again, the gravitational field is the same thing as acceleration due to gravity. So if they say surface acceleration, or what's the acceleration, or any kind of phrase like that, that's what they're talking about, is the value of g. Now let's start thinking about orbits. Elliptical orbits get a little bit funkier. We'll talk about them in a little bit, but for circular orbits, the centrifugal force here equation comes up, and then of course they'll ask about the period of an orbit, and then you got the circumference of a circle divided by your speed. Those are the things that are going to be important here when we're talking about circular orbits. Let's first deal with the question of orbital velocity. How fast is something moving when it's in orbit? Well, the force that holds something in an orbit is the force of gravity. If it's moving in a circle, then we can set the gravitational force equal to the centrifugal force, which is this bit right here. Solve that for v, and you have the orbital speed of an object in a circular orbit. The next thing we're going to do is we're going to try and relate the period to the orbital radius. And the idea here is, well, the period and the radius are related like that. Well, the speed is also related to the radius. So what we should be able to do is derive an equation which relates only period and radius and some necessary constants, but leaves out the v, right? It's t in terms of r. All right, let's see if we can make that happen. First thing is I don't really want to deal with the fact that v equals root gm over r. So I took a step back and I squared that and got v squared is gm over r. And then so that I can actually like plug that into my period equation, I'm squaring both sides of the equation and getting what's written below. Now we just gotta substitute that in. We'll have a fraction over a fraction, but that's easily dealt with. And if you like, you can do the rest of the algebra yourself, but what we end up with is t squared equals all this stuff over here, which turns out to be basically Kepler's third law of planetary motion. Okay, well, sort of. Remember, Kepler's laws relate to elliptical orbits, more on that momentarily, which means that r is maybe not actually the right variable. Instead, remember, we'll have, in fact, the letter a, which, what does that stand for? Well, it's probably been a little while since you talked about ellipses, so let's start talking about Kepler's laws, and we'll circle back around to this equation so that you understand it fully. Kepler has 3 laws. The first one is that planets move in elliptical orbits around the sun. Kepler could have universally applied this to anything. Any orbit pretty much whatsoever is going to be some sort of an ellipse. If we're describing the geometry of an ellipse, the long way across is called the major axis. This distance is the minor axis, but it's also actually not that important. So that's the last I'm going to say about it. The major axis technically is not even actually the important one either, though. It's actually the semi-major axis, which is half of the major axis, and that is represented by the letter A. The sun in an orbit, if we're talking about planets in our solar system, is always at what's called a focus of an ellipse. There are always 2 foci. The sun is always located at 1. The other is frankly nowhere special, except, of course, to the extent that mathematically it's the other focus of the ellipse, but there's nothing special located there. If you like, you could say that the semi-major axis of an ellipse is analogous to the radius of a circle. And also it's worth mentioning that, by the way, a circle is a special ellipse where the 2 foci are actually both in the same mathematical location, which is to say the center. So if there's only really one focus, that's a circle. So a circle is just a special case of an ellipse. For any elliptical orbit, since the sun is not in the center of the ellipse, but very much off-center, or maybe only a little off-center, but whatever, it's closer to one side than the other, there's always 2 locations that are of significance. The perihelion is when you're closest, the aphelion is when you're furthest away in that orbit. You are not expected by the AP to know those names. They will not ask, what's the name of this position, right? On the other hand, you really ought to know, like, where is perihelion, just as like a scientifically literate person. The perihelion distance in my diagram I'm referring to as R1. Aphelion distance is R2 because of how ellipses work. Since A is halfway across, 2A is the whole way across, and therefore add up perihelion and aphelion and you get this equation, which ends up being super useful when you're solving Kepler's law problems, where they're giving you, say, the perihelion and aphelion distance and asking for something like the orbital period, which is not an uncommon gravitation question. That should be all we need to know about the geometry of ellipses, so let's go on and talk about Kepler's second law of planetary motion. Kepler's second law, at first glance, is just kind of like a, well, that's neat, cool, man, kind of a law. So he's talking about how a planet, if you draw a radial vector from the planet to the sun and you look at the area swept out by that radial vector, if you're looking at, say, like a 1-month period or whatever, any particular period of time, the area swept out by that radial vector is the same in some given amount of time. Okay, so what, Kepler? That's neat, but what does this mean? Well, it turns out what it means is that planets don't move at a constant speed when they're going through an elliptical orbit. When a planet is closest to the sun, it's moving fastest, so that's perihelion, and when it's furthest away at aphelion, then it's going the slowest. That is the consequence of those two areas being the same, right? If this arc is longer, it must be moving faster than it is over there, since this arc is much, much shorter. Makes sense. But you still might be saying, okay, so what? It speeds up, slow down. Like, I need to have something mathematical that I can do with that. Yes, we do. The reason they speed up and slow down like this is because of really two things: conservation of energy and conservation of angular momentum. This law is actually most easily expressed with conservation of angular momentum. If we were looking at other positions besides perihelion and aphelion, the fact that this is in fact a cross product would matter, but they're only ever going to ask about perihelion and aphelion. Otherwise, it gets too gross to try and figure out, like, what is theta in this function. So essentially then Kepler's second law, mathematically anyway, boils down to that statement right there, that it's going faster when it's closer and slower when it's further away. And here it is again, Kepler's third law, but now you understand why A and R are essentially interchangeable as long as you're talking about a circular orbit, and also why it's A when we happen to be talking about an elliptical orbit and what that refers to. Okay, please remember the A is not for acceleration. You guys should be good with that, right? That's the semi-major axis of the ellipse. Okay, next up is orbital mechanics, by which we mean things like how much energy is there in an orbit, how fast do I have to go in order to get away entirely from the planet, what if I want a satellite to transition from like one orbit to another, how much energy do I have to put in, how long do we fire the thrusters, in what direction. All right, we're not going to get into all the complexities of orbital mechanics, right? And maybe someday you'll work for NASA and you'll have to really get into that. We're mostly just going to focus on the basics here of like energy of an orbit, escape velocity, and work needed to move from one orbit to another. So first of all, when you're looking at an orbit, there's two things conserved during that orbit. They are energy and angular momentum. If something's moving in a circular orbit, then we don't have to get that fussy about it, because the speed of it is going to be a constant. But there's a type of problem where they'll give you an elliptical orbit and ask you things like, listen, at perihelion it's here, at aphelion it's over here. Tell me how fast it's moving at each of those two positions. Oh boy, all right, that's a tricky one. And it involves kind of a bit of math, right? You got to write one equation for conservation of energy, one for conservation of angular momentum, and then we'll kind of have to plug in from there. One thing I do want to remark on while I'm thinking about it, in a lot of our equations here, there's this R thing that gets thrown in. Be careful with R. R is not always what it seems to be. They will frequently give you things like the altitude. Oh, okay, altitude, right? That's R. No, the altitude's not R. I'm sorry. That would be, for example, like the height that something is above a planet. And then you would have to maybe add in the radius of the planet. And those two things taken together might be the orbital radius if you're talking about, say, a satellite. All right, the radius of the sun doesn't matter if you're talking about that kind of an orbit, right? All orbits of anything around the sun are way, way bigger in scale than the radius of the sun. But for questions about satellites around planets and things, then this particular little shenanigan is going to get played on you all the time. So just be alert for that. If they give you an altitude, that's not the orbital radius. That needs to be added on to the radius of the planet. Okay, moving on. So if they give you this direction, find the speed at those two positions, here's your procedure. Ideally, you can just use conservation of angular momentum because it's so easy, right? If they tell you the speed here, the radius, also the speed here, and they want to know like the other radius. Oh man, you know 3 out of 4 things. Oh, that's great. And then you plug in what you know. All right, now if you are only told, oh no, I'm told like just the 2 radii, or maybe the 2 speeds, whatever it may be, then you have a little bit more work ahead of you. In that case, you're going to have to also use conservation of energy. Now, if you want to understand why this equation is gravitational potential energy, you should go back and watch the other video on my YouTube channel about gravitational potential energy, and it'll go through all the nitty-gritty of like, why is it a negative sign? How is this okay? But I thought it was MGH, and you lied to us, Mr. Errico. You lied! Okay, calm down. Yeah, it's a little bit not that close to MGH. I agree. It doesn't look like it. But that is actually the correct formula for gravitational potential energy, whereas MGH is only an approximation. If you try using MGH for orbital mechanics, it will fail massively. So don't do it. The other super important thing is, again, this negative sign. There's a negative sign there. Don't forget it. Gravitational potential energy is always negative if you're anywhere reasonably close to a massive object, right? So it's negative here. It's less negative out there, right? So B would be, say, even less negative. Ooh, very less negative over here. What about at the surface? Isn't it 0 at the surface? No, it is not. It's very negative at the surface. All right, it's the most negative it can be unless you start like drilling down inside of the planet. The only place where the potential energy is 0 is infinitely far away. Okay, so don't forget that negative sign. Use the right formula. All right, from this point though, it would be a lot of algebra. I'm, in this video, not going to go through all the algebra. I'm just trying to remind you of sort of the scope of the problem, right? From here, it would be nitty-gritty algebra. Plug in the things you know, so probably it would be good to practice it with some problem. Find a book problem that looks like it might be about this sort of thing, or an AP problem that's about this sort of thing. But yeah, from here it's algebra. As long as you know you're using these 2 formulas and you can do algebra, which I know you all can, then you should be able to solve it. All right, what about find the mechanical energy of an orbit? Well, if something's in orbit, remember the mechanical energy is constant. We just talked about that. And so if you just want to know how much energy is there in that orbit, well, that's the matter of, let's see, at any particular position it's moving. It's also got a certain amount of gravitational potential energy, which changes based on position, as does the kinetic energy. But if you can figure out those 2 things and add them up, that's the mechanical energy. The least intuitive result here, though, is that the mechanical energy of an orbit is always negative. Always. What if it's going really fast? Then it's not in orbit. If it's going fast enough that E mechanical comes out positive, it's not in orbit. It's actually escaped. It's never coming back, which is not an orbit, right? An orbit means it's stuck going around. So the mechanical energy should always be negative, and I can prove it. So here's my proof. We'll do this for a circular orbit, and I'm sure there's a fancier proof for doing it for any orbit, but we'll start with there's our equation. If it's in a circular orbit, then for V, we can plug in this root gm over r equation that we derived way earlier in this video, which after squaring is going to give us this result. And after combining, find a common denominator combining like terms, we're going to get, negative GMM over 2R. That's weird. So yeah, it's always negative. If you want to know the mechanical energy of an elliptical orbit, by the way, instead of an R, it's an A. That's actually the only difference. However, on the AP, if they say find the mechanical energy for an elliptical orbit, they're probably going to give you the speed and the distance, or have asked you to already figure those out, and they will expect you to go through this whole process with like plugging in particular values. You won't be able to just say negative GMM over 2A. But that is actually also always the mechanical energy of the orbit, and you can check that. But they will kind of hyper-focus on that negative sign. There's always one point for this kind of a question where it's Did they say negative in their answer? Good. All right, that's a point. So just write down a negative number if all else fails, and you're going to get that answer point. All right, what about find the work to like move something from one orbit to another? Well, I'm not going to spend a lot of time here. This just naturally builds off of what we just talked about. If you can figure out the mechanical energy for this orbit, and then they want to know about the mechanical energy, or the work done rather, to get something into that orbit, it's just a matter of find the mechanical energies of those two orbits. And then what's the difference between them? And that's the amount of work that you'd have to do with your rocket engines. All right, now escape velocity. This one features on multiple choice often because it's just like a real quick, write an equation down, plug numbers into it, what's the escape velocity? Now, when we think about escape velocity, or rather minimum escape velocity is their term for it, the idea is that you're going away and never coming back, which means coasting to r equals infinity, which means that you would have to be, reaching a final gravitational potential energy of 0, because at that point you really have got away. You're infinitely far away. That's away. And also, if it's the minimum escape velocity, that you are coming to rest there. So your final kinetic energy when you reach infinity is 0. Well, that means the total mechanical energy is, 0. That's it. Okay, plugging in the formulas for kinetic and gravitational potential energy, we can solve for V escape. And we get this equation, root 2gm over r, which looks similar, by the way, to the equation for orbital velocity. It's just got this 2 in there. Don't make too much significance out of that fact. It's got a similar structure. That's kind of interesting. But what it does sort of mean is that if something is in orbit, wherever it is, it just has to go root 2 times faster than it's going, and it will escape. Okay, so that's kind of interesting. Other than that, I don't think there's too much to say about the relationship between those formulas, but this is a good one to know because on the multiple choice, they might just ask you for escape velocity or ask you to compare escape velocities for like 2 hypothetical planets. All right, now, to sort of round things out, one weird problem, the binary system. What do we do if we have 2 stars that are in orbit around each other? For simplicity, I've given you 2 that are of identical mass. If they're not of identical mass, then the orbits would be a little bit different. The weird thing here is that they orbit around their center of mass, which is, of course, halfway in between them if they're equal masses. If they were unequal masses, then they would still orbit around their center of mass, but then that would mean that they would move in 2 different size circles. Okay, now that we're not going to talk about that particular issue. We're going to focus in on equal masses and how would we find orbital speed and orbital period and that kind of thing. Well, we would do it the same way as we did before, right? We would say it's the force of gravity, which makes them, stay moving in a circle, and it's a circle. So, centrifugal force. So we can just set them equal to each other, right? And if you think about it, we'll end up getting V equals root GM over R. Again, actually, that's wrong. And the problem with this comes in when we think about what do we mean by R in each of these equations. We don't mean the same thing. The R for the gravitational force formula would actually be, we're going to call it 2R, where R is the radius of the circle. But the R in the gravitational force formula is the center-to-center distance, which is the diameter of the circle. Tricky. So that means that the R that we plug in will be the diameter. Okay, so 2R. All right, and then the masses, of course, are the same for the 2 objects. So a little bit of algebra, and we get this formula. Okay, so 1/2 root GM over R. So kind of similar looking, but different result because of the difference in the meaning in R there. All right, let's see if we can figure out the period. Getting the period would again be 2 pi r over v since they're moving in circles. when I plug in my new formula for V, I'm going to get this. Notice the 4 up there because of the 1/2 and that fraction over fraction algebra thing. So actually that's a good enough equation, I suppose, as long as I know like what V is. But if I wanted to, I could rearrange it and get this, which is sort of like a new kind of Kepler's third law, but with like a 16 there instead of a 4. Okay, now this is a weird-ish problem, right? We didn't have to do any like this in honors. Binary star systems are funky. But notice, as long as we're careful, we can analyze it using the same kinds of things with which we would analyze any circular orbit. And that's, gravitational force and centrifugal force and the formula for a period. We just have to make sure that we are careful about understanding what is meant by R in each of those equations.